Okay, so we have seen how the set of piecewise continuous functions on some interval a comma b, it forms a vector space. So in this lecture, we will see how there is a natural basis, for this kind of a vector space. So we will fix our interval to be minus pi to plus pi. Later on, we will look at how this can be generalized to other intervals, and then we will see how naturally from this sort of linear algebra perspective we would get to the Fourier series. And in fact, in this lecture, we will provide a prescription for how we can take a function which is periodic, and we will be able to expand in terms of a Fourier series. Right, so suppose f of x is a periodic function with period 2 pi. We want to be able to expand this function in terms of sine of n of x and cosine of n of x. Right, so this is a reasonable expectation, since for all integer values we know that sine nx and cos nx, they form their functions with period 2 pi. But in fact, we will argue that these functions in fact form a basis, and they're not only a basis but they are an orthogonal basis, right? So our goal is to be able to write this function f of x as half a naught plus, I'm calling this as half a naught for a reason which will become clear later on when we write down the prescription for these coefficients. So we want to see if there is a way to work out these coefficients, half a naught plus a1 cos x, so on, so that we'll be able to write this series expansion for this function. Given a periodic function f of x, will we be able to write down an expansion of this kind, right? So so we need a prescription to work this out. So in order to proceed, so let's first work out a few integrals, right? So the periodicity is needed, is needed because we are going to think of this function as stretching out for all values of x, but in fact all the action is just one period. We have seen that the average of a periodic function is the same no matter in which interval or equal to the period length it is taken, right? So we in that sense, so we would be able to focus all our attention on some one period, and all the information about the function is known, right? So let's see how cosines and sines form an orthonormal basis for piecewise continuous functions in the interval minus pi to plus pi. And so it's some period of length 2 pi is good enough, but let's say we look at the region from minus pi to plus pi for concreteness, right? So if we denote the vectors sm as sine of mx and cn as cosine of nx, so let us work out the following inner products. So we already defined this inner product as this integral, right? And so we will work out these inner products, right? So before we do that, let's plot a few functions. Suppose if I plot sine x into cosine 2x in the interval minus pi to plus pi, it's going to look like this. So you see, I'm interested in finding out this integral from here all the way up to here. So if you look closely, then you see that this function is symmetric, right, or anti-symmetric if you wish, right? So it's spent equal time above as it does below, and in a mirror image manner. So just looking at this visually, you would expect that this integral is actually going to go to 0, and in fact that is true, as we will argue. And that is also true for sine x times sine 2x. If I take the product of a sine with another sine with two different integers here, by one here and 2 here, you can play this game with many other functions. Instead of sine x and sine 2x, you can try out how the function looks if you do sine 10x times sine 15x, whatever you want, and then you will see that indeed again this part will cancel with this. If I were to integrate this entire period, this part will cancel with this, and this is going to be 0. So, and likewise, what about if I look at cosine and cosine x times cosine 2x? Once again, you will see that there is a way to consider mirror images. So this is some part, whatever part which lies above, that part you can make this go away with this part, and then there's an upper, this part will go away with this and this part will go away with this. So if you were to integrate this, you would expect that this integral of this function also will give you 0. So in fact, you can use trigonometric identities and show the following results, which will be homework. I will allow you to work this out using trigonometric identities, right? So I have just shown you pictorially or visually why this would play out, but you do the more rigorous way of showing this. So if I take the inner product Sm with Cn, I have to do minus pi to plus pi sine of mx cosine of nx dx. It's going to be 0 no matter what m is, no matter what n is. But this Sn, this integral, this inner product is going to be 0 if m is not equal to 0, or if m equal to 0 and m equal to 0 equal to 0, right? So then it's obviously going to be 0 because you're integrating just 0. But on the other hand, if m equal to n, you will get a pi, right? So this will in fact go back to the integral sine squared, which we did a few lectures ago. And likewise, when you do integral of cosine of mx times cosine nx dx, the inner product of Cm with Cn, you would get a 0 if m is not equal to n. But you would get, if m equal to n, again there are two further cases you have to make. If m equal to n equal to 0, then you're integrating 1 from minus pi to plus pi, so it will going to be 2 pi. But on the other hand, if you're integrating cos squared x dx, for example, let's say, then it's the same as sine squared x dx, and then you'll get a pi. If m equal to n not equal to 0, then you get a pi, right? All of this is for you to work out, using trigonometric identities directly. So the point of what I am doing here is to show that if I, so there are two things which I'm trying to say, right? One is that if I consider a function which is periodic, right? So I'm going to restrict my attention to just one period from minus pi to plus pi, and within this period, this function is a piecewise continuous function, and it's a vector which is a part of this space, this vector space that I have said, right? So it's profitable to think of this vector space perspective, right? Although we could have just gone ahead and done the algebra and worked this out directly from just trigonometric identities and so on. I'm just telling you that what is going on here is also there is a vector space way of thinking about this. So in fact, all these cosine x's and sine x's, according to what we have just shown, they are orthogonal to each other, right? So we can also make it orthonormal. Then you'll have to make redefine these vectors with some factors. So let's not do that. So let's leave these pi's and 2 pi's and so on, let them be there. But the key point is that if you take any two of these vectors and take the inner product of them, then you get 0. So they are all orthogonal. And so what is the meaning of this? The fact that you can take any vector which belongs to this space and expand it in terms of all of this is an indication that this is a basis. So in fact, this is an orthogonal basis for this space, and that's what Fourier series really is, right? So let's work out these coefficients now, by looking at a pattern. So if we have this, if we compute minus pi to pi 1 over pi f of x dx, so then what happens? So we have this expansion on the right hand side. Because of the above result, we see that since all of these functions on the right hand side, cosines integrated in one period, sines integrated in one period, they all give you 0, and so the only term which will remain is the constant term, which will give you just a naught. So in fact, a naught is the average of your function, subject to this. There is a factor of 2 which we have introduced, right? So you have to be careful. So basically the point is that the constant term is the average of your function. And then you have integral minus pi to pi f of x. If you tag along a cosine of x dx and then you do this integral, then you can quickly show that every term except the this term involving cosine, where cosine x goes along with cosine x and it lives, whereas because of this result that we have had, right, they're all orthogonal to each other, every other term will vanish, and so you get a1, right? You can check this, that this integral will give you a1. And likewise we can check that in fact if you do this integral f of x with sine of x, you multiply with sine of x and then do the integral, every term except the one with sine of x will vanish because of this property of orthogonality, and this will give you just b1, right? So this is a pattern which you should carefully check, you know what I have done, all the algebra here, and in fact this will extend, which also is something that you should directly work out. And what we see is, if you want the nth coefficient an, you just simply have to multiply f of x with cosine of nx, and what it does is, because of, and then integrate in the period minus pi to pi, and what it will do is it will annihilate, or it will destroy every other term, and it will only selectively choose the term that you're interested in and work out for you the coefficient, right? So in some sense this is just taking an inner product of your vector with the basis vector of your choice, right? That's what is going on, right? So it helps to think of this from the point of view of, you know, vector spaces, and so you get an and bn. So now you see that you have this compact expressions for an and bn, right? That's why we wrote a naught by 2 instead of just a naught for the constant term, right? So that we have this one nice formula, it's easy to remember, right? So what we have managed to show in this lecture is that, you know, Fourier series expansion of a periodic function with period 2 pi in terms of cosines and sines, you know, is there. We have provided a prescription for this, we have worked out the coefficients, and we have also argued that really the Fourier series expansion is actually an expansion of a vector in terms of its in terms of an orthonormal you know, basis, right? So where sines and cosines should be thought of as providing a basis for this vector space. Okay, that's all for this lecture. Thank you.